Chapter 7, Linear Regression. So when we're talking about our observed values or the actual data from our data set, we use the notation y. That's our response variable. So the y is going to correspond to the actual values in our data set. When we're talking about the predicted values that are the output from our model, we're going to use this notation that's called y hat. Okay, so y hat is the predicted value, y is the actual value. We're also going to be working with these elements called residuals. And the residual is the difference between the observed value and the predicted value. So your residual is going to equal your observed value minus your predicted value, or y minus y hat. Now when your residual is positive, your model is under-predicting at that point. And your residual is negative, the model is over-predicting at that point. So we use the residuals to measure the fit of our line against our data. So a line that fits well will have small residuals. And we want to summarize the individual residuals into one number. Okay, so what we do is we take each data point and we subtract off the predicted value. Okay, we square those and then we add them all together. Okay, that gives us all of our residuals in one number. Now the least squares line is a unique line that makes the sum of the squared residuals as small as it can be. It's also known as the LSRL, or the line of best fit. So this slide shows the generic form of the linear regression model. So what we have here is our predicted value of y, or our y hat, equals b naught plus b1 times x. Now b naught represents the y-intercept. That's the value of y hat where it crosses the y-axis. And b1 represents the slope. So the way that you would find the slope is you take your correlation coefficient r and you multiply that by the standard deviation of your y's divided by the standard deviation of your x's. Now to find the y-intercept, your b naught, that is equal to the mean of your y values minus your slope times the mean of your x values. So when we interpret the slope is going to be described as an average, an estimate, or a prediction, and the change in y is linked to a change in x. So for example, we would say something like an average change in y based off of a particular change in x, or an estimated change in y dependent on a particular change in x. Now when we're interpreting the intercept is the predicted value of y when the x is 0. So let's go back and talk about residuals for just a moment. Now remember, your residual is your observed value minus your predicted value. Okay, and it's represented by E equals y minus your y hat. Now when we're working with linear regression, we want to look at a scatter plot of the residuals. Okay, so this scatter plot of residuals should not have any direction or shape, okay, and it should show about the same amount of scatter throughout without any bends or outliers or patterns or anything like that. Well, just like we had talked about earlier as far as standardizing the values in our data set, we can also standardize our error values or our residual values. Okay, this standard error summarizes the typical residual size. And it's important to look at the residual plot to confirm that residuals do not have a tendency to grow or shrink as you go from low x values to high x values. That's what I had mentioned on the previous slide. We don't want to see any pattern in our residual plot. So the distribution of the residuals should be consistent with a normal distribution, which implies that 95% of the model's estimated y values, or y hat, are within 2 standard errors of their corresponding actual y values. So earlier we had talked about R, which was our correlation coefficient. This particular variable here, r squared, is what's known as the coefficient of determination. And what it does is it measures and quantifies the variability in the data that is explained by the model. So if you were to calculate an r squared and it equaled 0%, that means your model explained no variability in y, and in that case your model is useless. If your r squared is 100%, your model explained all of the variability and the model predicted all y values perfectly. In reality, that is extremely rare, if ever. Okay, you're not going to have a model that explains all of the variability in y. If you remember back in chapter 1, we talked about statistics was one of the goals was to explain variability. Well, some variability we can explain, some variability we can't. So don't expect to get r squared values of 100%. It would be extremely, extremely rare, if ever. Now, r squared is defined by the variability in ry hat divided by the variability of ry. And your r squared, expressed as a percentage, is going to be between 0% and 100%.